So good morning everyone, welcome to the penultimate day's lecture, this workshop. Today we are very fortunate to have Dr. Vasudevan from IBM Research Labs in India. He was, by the way, earlier in Australia. Very nice for him to come back to India. So to give a bit of a background on Dr. Vasudevan, he did his his BE actually. He's from a computer science and engineering background from the University of Madras in 2002, and then went on to do his MS in University of Southern California in 2004 with an emphasis in intelligent robotics, and then pursued the same subject to complete his PhD from ETH Zurich in 2008. And he is now obviously at IBM Research Labs in India, and he does a lot of very nice things, including data fusion, pattern classification, machine learning with complex data, particularly from data where data comes from heterogeneous sources, and all of these with applications in robotics, in artificial intelligence. So let's give a big hand to him for coming here. And I'm sure that we'll have two very interesting lectures today. So, Dr. Vasudevan, please.
Thank you for the very nice introduction. Thank you for having me here. I'm really pleased to be here. So I want to talk a little bit about uncertainty quantification in machine learning applications. Okay, I've had quite a few different experiences in different domains over the years. I want to share that with you. I've kind of got an agenda planned out. Don't know if I'll be able to squeeze in everything. That depends on how long different elements take. But if we can, obviously the first part is going to be important. I mean, you'll have a very significant chunk, probably the entire lecture, the first one, on Gaussian processes. Okay. We'll discuss how we model data sets, as how we can also integrate different data sets using this particular technique. It's an incredibly flexible, very powerful approach. I think you'll enjoy it. Okay. So I had the option of going deeper on Gaussian processes as well as going broader. I chose to go broader because going deeper requires more time, and I don't want to drown you in detail. I want you to take away key concepts or key ideas and make them your own by kind of learning it yourself. So so I, instead of just showing you GPs, I will also show you how uncertainty is handled in, for example, in robotics. A couple of different problems over there. You will get a flavor of different problems, different things, how things are done. Okay, and more recently, I've also been so you might know that AI and deep learning and deep neural networks is the big hype of the day. Okay, so recently I've also been looking at uncertainty in that domain. Okay, so I'll share some preliminary forays into that area. Okay, and all of them, at least my efforts in all of these areas, okay, are connected by the Bayesian modeling paradigm. So if we manage to get that far, covering all of the elements, I'll link them together. Okay, with that one paradigm. Okay, it's important for me to kind of clarify what I am going to talk to you about today and what I'm not. Okay, so what these talks are not are a theoretical presentation. I will not drown you in detail. Okay, I intend to give you applications. I will show you. I will motivate my different concepts through real world applications. Okay, and I'll give you a sufficient introduction of those concepts. Okay, thereafter, if you are actually interested in these concepts, you will go and you will do your own self study and make it your own. Okay, I'll give you a broad introduction to all of these concepts. That's basically what I'm going to do. Okay, so and I'll also touch upon many different domains. Okay, so you will see examples from mining, from AI, from oil and gas, from robotics, a lot of different areas. Okay, all of them will have one thread in common, which will basically be uncertainty. Okay, and how we handle it. Okay, that's kind of the emphasis of this whole winter school. Okay, so with that, let's start with the first one. Okay, so we'll start with modeling and information fusion with GPs. Okay, so a quick word of acknowledgement. This is work which has gone on for a very long time. I started this back in 2008, early 2008. It's gone on over the years, it started in this Rio Tinto Center for Mine Automation. Rio Tinto, by the way, is one of the largest mining companies in the world. So they established a center, okay, in a university dedicated to this effort, okay, and this kind of gone on with over different labs and different areas, okay. A lot of wonderful collaborators I've worked with. So some nice experiences along. Now, to kind of give you a motivation, okay. This isn't something I pulled off the net, okay. This is a panorama that I took from a site where I was, okay. So imagine you're at one of these locations. This is a mine site, a proper mine site in the middle of Australia, in the middle of nowhere, to be honest. Yeah, so if you're asked to automate this mine, okay, what would you do? So especially if you're given that vehicles like this are roaming around, and the intended application, okay, is that these vehicles have to be able to move without a driver, okay? So the intended application is a completely autonomous mine, okay? Our background in robotics means we are good at, automating these machines, but automating machines is one thing, and giving them the tools to actually navigate or do things is another thing altogether. So our mandate in this center was basically information automation, not vehicle automation, information automation, okay? So again, if you look at this picture, okay, if you have that sort of a truck moving in this sort of an environment, if you don't have a good terrain model, for example, okay, it's going to fall off, and you're going to lose lots of money, okay? If you are digging, iron ore or coal or whatever from this sort of an environment, okay, as a geologist, okay, you want to know where the ore is, okay? If you actually dig down, it's a very, very costly exercise, okay? You can only take so many samples, okay? Can you, okay, create a reasonably accurate picture of the subsurface geology so that you can actually efficiently, go about digging? Don't go and dig in places where there's nothing. Go and dig in places where there is, you can expect to find some more, okay? So making that efficient, okay, requires some sort of good subsurface modeling, okay? There are other applications too, but I'll concentrate on these two, okay? Yeah, so that was a little bit of motivation, okay? Basically in this talk, we'll talk about Gaussian process modeling, okay? We'll talk about kernels, okay? We'll talk about GP learning. How do you learn GPs, okay? How do you handle really large data sets, okay? Or how we did it, okay? And we'll also talk about data fusion, okay? So I'll kind of bring about, I'll explain in what scenarios you require data fusion, why you need it, okay? And how you can go about doing it, okay? We'll look at several applications of GPs. So it won't be a single, theory lecture. I'll talk about a few concepts. I'll show you a bunch of applications where they've been applied. Without going into too much of detail, but you can go and look at the papers if you want to, look at further detail on any of them. We'll also introduce how GPs can be used for classification problems, okay? How we can, so there will be some complexities over there. So, how do we approximate certain complex distributions? We'll look at it over there, and how we can use GPs to extend it to, to address other kinds of problems. We'll look at all of that in this lecture. Okay, so this is kind of what I just showed you. This is a small snapshot, a small piece, if you like, of the data that you get from that mine site. Okay, so the way we get this data is typically we have a laser scanner, okay, which basically shoots out a bunch of laser beams, and it gets those laser beams back. And by using time of flight techniques, you can kind of estimate, different points, how far they are from you. So you can kind of reconstruct this data set. If you also have a camera attached to it, you will get your RGB color. Okay, that's how this thing is put up. The only difference is that the sensor that we used was itself cost more than $250,000. Okay, so yeah. If you look at this data set, okay, what's interesting is that you have this data set where you have both rough surfaces as well as flat surfaces. You have gaps, and no sensor, no matter how costly it is accurate. Is absolutely accurate. So every sensor has some level of inaccuracy. So how are you going to model uncertain data, correlated data? So given that points are part of the same surface, okay, they are obviously correlated. So if you have information, if you can use that correlation, you could potentially fill up those gaps. Okay, yeah, and you have incomplete data, obviously. So how do you go about dealing with such data? Okay, look at another application. It need not be only a mine site. Okay, you might be doing stock trading. You might be modeling currency. You will have time series. You'll have different, indices that you'll be tracking. Okay, they are obviously correlated. There are events which affect different indices, all in different ways. Can you model them? Can you exploit those correlations? Okay, here's a typical application of what I just spoke about in the context of subsurface. Okay, so this is a case where we actually go and get samples from the subsurface. Okay, we can do that in a limited area. Okay, and you're seeing two different elements. Okay, there are many elements which are of interest. The question is, all of these elements are correlated. They are part of the same subsurface. Okay, you can model them independently. Okay, and you can also model them together. If you model them together, you typically get better outcomes. Okay, so can you create a model of the subsurface geology that is more accurate than what you can do now? Okay, those are the kinds of questions we are asking. So with that's the introduction I want to give you into why we go into GPs. Okay. In brief, I think you guys know all this, okay? But you know what a univariate Gaussian is, okay? You have a random variable that takes that particular form. I'm not going to go too much into formal specifications. I need you to get the message. That's really all I want, okay? So that's your random variable, that's the form it takes, and that's the kind of shape that distribution is going to have. You know that, right? Now, if you have a multivariate distribution, okay, when you have multivariate random variable, you're going to have a shape that looks like that. You're all happy with that, right? Okay. So the important elements here is that it's specified by a mean vector, okay, and then this covariance matrix. Okay. So we know what a Gaussian over a univariate Gaussian is. We know what a multivariate Gaussian is. So what is a Gaussian process? Okay. We'll get to that in just a minute. We just need some additional properties. So I will keep coming back to these properties in many of the aspects that I cover, okay? So it's important to note that conditionals and marginals of a Gaussian are Gaussian. So if you can look at that first equation over here, I press that one, yes. So this, if you have x and y are jointly Gaussian distributed with a mean of mu x, mu y, okay, with this block covariance matrix of, whatever A, C, C transpose B, if you get the conditionals and the marginals of it, okay, it is standard formula which you can look up from, for example, here. Okay, you can derive it also, but you can actually look it up from here. Okay, they are Gaussian distributed. Essentially, that's the Scher complement. Okay, and it boils down to using those things, and you can specify both x given y and y given x. They will be Gaussian distributed with a certain mean, mu x, mu y, and the Scher complement over here. Okay, so this is stuff that you need to note. Okay, and the other thing you want to note is that sums and products of Gaussians are also Gaussian. Okay, we'll keep using these implicitly. Okay, the product obviously takes a slightly more complicated form, but nevertheless. Okay, you can again look up these formulas in this particular reference. Now, given this background, okay, a GP is basically a stochastic process. Okay, it's a collection of random variables, any finite subset of which are Gaussian distributed. So we know what a Gaussian over scalars is. We know what a Gaussian over vectors is. Okay, now we have a Gaussian over functions. Okay, and I'll kind of explain that with a picture. It'll become much more clear. Okay, so it's important to note that there is a mean function. Like we have a mean and a covariance matrix. Here we have a mean function and a covariance function that specify a GP. Okay, now. This image I've taken from a classic reference on GPs by Carl Rasmussen. Okay, the references are here. The slides will probably go online. Okay, and you can pick it up from there. It's a classic book. Okay, it was my first reference into this topic. Basically, let's have a look at this. So when I say a Gaussian over functions, okay, does that become clear to you? Easy? Okay, it was for me too. Okay, so one way of thinking about it is this. Okay, it's a simple way of looking at it. Imagine you have a bunch of random variables lined up from -5 to 5. Okay, these random variables can take some values along the y dimension, which is my f of x. Okay, each of these random variables is Gaussian distributed. So think of a Gaussian that's vertically laid out. Okay, at each of these points. Now I take samples. Okay, I sample each of these random variables. So for the point at -4, I get a point maybe here. Okay, and the point at -3, I get another point over here. You line all of them up. That's one function. That's the green one. Okay, you do that other times. You might get the red curve. You might get the blue curve, so on and so forth. Okay, so you have infinitely many such curves. There's not 3. 3 is just one sample over here. You have infinitely many curves over here that GP represents. Okay, that gray area is the uncertainty. As I said, like every Gaussian, okay, you have an uncertainty vector over a matrix. Okay, so that specifies the uncertainty over the function space. Okay, so till now, what you know is that a GP is a family of functions. Okay, it's a collection of functions. That's basically what it represents. It doesn't. So when you talk of it's called a non-parametric model. Okay, for a reason. So if I were to specify a parametric model, what is a parametric model? So if I'm actually fitting a line, okay, so y equal to mx plus c. Okay, my m and c have definite values. Okay, you actually can use the points, estimate those values. Fine. In this particular case, I don't specify one particular curve. I don't specify one function. I have a family of functions. So how do I go about specifying it? You need data. Without data, a GP is just a collection of functions, a family of functions. Okay, it's the data when it comes in. Okay, what you're doing is effectively by modeling the GP for a given data set, you're picking from this big family of functions those functions that fit all your data points. Does that come across? Yeah? You guys are bright. It took me a long time to figure this out. Okay. Yeah. So it sounds easy when you say Gaussian over functions, but it's another thing to understand it, visualize it, and yeah. Anyways, some properties of GPs. Okay. If you what you're doing with a GP. Look, let's come back to this figure. Okay, you have a bunch of points, right? You're picking from this family of functions a subset that's passing through these points. Okay. What you're effectively doing is you're trying to use these few plus marks, the points, okay, to find a continuous manifold through all of them. Okay. So once you have this continuous manifold, red, green, blue, whichever line you pick, okay, you can sample at any resolution you want. Okay, you started off with only these plus marks. Using only them, okay, you don't have very much of an information. From that, I try to, you try to learn the underlying functions that represent those points, that can represent those points. And once you have those continuous manifolds, you can sample in any resolution you want. You want to upsample, you want to downsample, no problem. Okay, so yeah, so what you're doing is you're learning a continuous representation, and you can sample at any desired resolution. Yeah, you have. Yeah.
The previous slide.
Let's go.
Are you always sure that we will get curves which pass through all these points?
Yes, by learning the GP, when you learn the GP, you are effectively finding, you're trying to fine tune or tweak those parameters to pick only those functions that pass through this. By itself, it's the whole, set of functions. When you have a data set, that becomes you specify the, set of functions that go through it. It comes, when we do GP learning, it will become clear. Okay. Yeah, so the next thing that you need to understand, okay, is that you saw initially that the uncertainty was quite large. Okay, it's this whole gray area. Okay, any function in that space. Once you have data, you find that the uncertainty, if we can dim the lights, we'll be able to see this, but otherwise I don't know if you can see it, but the gray areas become smaller. Okay, the reason is, okay, that once you have data, the uncertainty about your, the functions that of your interest, okay, actually it comes down, and wherever you have data, the uncertainty is low. As you go away from data, the uncertainty automatically increases. So it is, what this is called is data-driven characterization of uncertainty. You allow the data to tell you how uncertain or certain you are about your predictions in different places. Okay? Now, because of the properties of Gaussians, which I referred to earlier, okay, every point in each of these curves, take any of these curves, any of these manifolds, okay, is effectively a linear function of each of these points. Some linear function. If maybe one linear function will give you some points on the green curve, one linear function might give you points on the blue curve. What that function is a different issue. We'll come to that. Okay, but the properties of Gaussians will give you that for you. Okay, so the important thing is, okay, that you are able to do data-driven characterization of uncertainty. Okay, and the third thing is we can estimate what we have. So using any of these curves, whether you use the red one or the blue one or the green one, you can estimate the plus marks again at those locations. If you were to make predictions at those points, you'd get back those points. You can also estimate the other points on those curves in terms of what you have. Okay, that's what a GP will give you. Okay, yeah. So this is some sort of upsampling, downsampling, and showing. So there are only 3 points which I actually have, and I actually see the uncertainty explode on both sides and decrease in between. So it's just a simple example of these ideas. Now, given this, okay, let's try to. I'll have few equations, but those few equations will be pretty useful stuff to understand GPs. Okay, so let's go back to the definition of GPs. What did I say? A collection of random variables, any finite subset of which will be jointly Gaussian distributed. I've written exactly that over here. Okay, sorry, I am not particularly comfortable with this, but yeah, yeah. So if you have X and Z, so I will keep using this terrain modeling example. Okay, so in the terrain modeling example, my X would be X comma Y, and my Z would be the elevation at that point. Okay, so if my X and Z, for example, are my given data, and X star and Z star are some points where I want to estimate what the elevations are. Okay, basically the Z and the Z F star together are jointly Gaussian distributed with a mean of 0, and I'll come to that. Okay, and a nice covariance matrix here, which basically captures the covariance between the training data and itself, the training data with the test data, the test data with the training data, and the test data with itself. Nothing else. Now, why is the mean 0? Not necessary. You can use some complex function over there. You can have a linear function as you wish. What we tend to do in practice is shift the data, the given data that we have, okay, so that the mean is 0. Makes life easy. That's all. Okay. What this kernel or covariance function K is, we'll look at it in the following slides. Essentially, like you have a covariance matrix, okay? You have a covariance function over here. We can apply different functions, which is where the power of GPs come in, okay? We basically quantify the correlation between different random variables. That's what we're doing. So how, so for example, if you're looking at spatial correlation, okay? How are points which are further away from me correlated with me? Those are the kinds of measures that these quantities capture. Okay. Now, given this joint Gaussian distribution, let's go back to the first property that we talked about. Okay, that conditionals and marginals of Gaussians are Gaussians, right? So we can basically find the conditional estimate of F star given Z. It will be Gaussian with a mean and uncertainty that is specified over here, which is exactly what you'll obtain if you plug in the formulas we looked at before. Okay. So what is important to note over here is if you look at this expression. Okay, at the test points, wherever you want to make an estimate, okay, whatever you're modeling, let's say you're modeling terrain, if you want to estimate the elevation at a certain point, okay, it is some matrix math, whatever matrix multiplication times z. Okay, what it means is that the estimates at unknown locations are a linear function of the estimates at the known locations. I told you earlier that every point will be a linear function, okay, some linear combination of the existing data. That becomes visible over here. Are you all with me on this? Yeah? Okay. Now, I also mentioned that every sensor, no matter how accurate, no matter how expensive it is, okay, is inaccurate, is inherently inaccurate. Okay? Maybe less uncertainty, maybe more uncertainty, but there's some uncertainty. Okay? So if you assume that your given data, okay, is noisy, okay, we can add additive Gaussian noise, okay, which basically would be something like, a Gaussian noise with a mean of 0 with some sigma n squared I variance. Okay, that sigma n, what it is, we will find out. We will learn all of that from data. Okay, but being a Gaussian, life is good. We can quite simply add it over here. Nothing happens. Okay, so this is one of the takeaways that you need to take from this lecture, that in a Gaussian world, okay, you can do things, you can manipulate things very easily, because Gaussians have been studied well enough, and there are enough closed form solutions, okay, for many different many different extensions, if you'd like. Okay, this again boils down to sum of Gaussians is a Gaussian. It comes back from that property. Okay, so if you have additive Gaussian noise, you just add a sigma n squared I term over here. You can also assume that your test points are as noisy as your training points. Reasonable assumption. Wherever I'm making a prediction, I will assume that my predictions are also having the same amount of noise. Okay, and add that sigma n squared I to the predictions also. Nothing else. Yeah.
also making matrix invertible, sigma square I. For adding the term sigma square I.
Yeah.
Isn't it for making the matrix invertible?
It is not for that. It is not for that. You could do that. So if you have a matrix that is having rank issues and so on and so forth, you could add something to the diagonal. We add a jitter, a small jitter, but typically that's a very, very small number, say 10 to the minus 10, something really small, okay, to just about make that inversion possible. But this one is to actually quantify noise.
But if we don't have, then we don't have means the form, closed form. We are not sure about the matrix invertible.
Okay, so good question. So this particular kernel function, okay, it is by definition, okay, we restrict it, okay, we have that restriction that it has to be positive semi-definite, okay. So here's the difference. Or we call this kernel or covariance function, okay, and in this talk I will go on interchangeably using kernels and covariance functions, but in principle a kernel can be a function of any kind of function, okay. There is no restriction. But a covariance function has to be necessarily positive semi-definite, okay? So all kernels need not be covariance functions. All covariance functions are by kernels, okay? Yeah. So you can be rest assured that this one has to be positive semi-definite, and this is an additional noise that you add, okay? Yeah. Now I believe you people have been exposed to kriging before, right? So in geostatistics, okay, there is a concept called kriging, which is very, very similar to what GPs do, okay? Kriging, okay, is basically also doing, estimation through linear combinations of existing observations, okay? So if you have points x1 to whatever xn, and you want to estimate this red point, okay, some linear combination, some weighted sum of these observations is what this will give you at the red point. It's a form of interpolation. It is the de facto standard interpolation technique used in mining and other related domains, natural resources and all of those domains. Okay, the question is how are these weights computed? Okay, in the kriging paradigm, okay, what people do is what's called linear least squared estimation. Okay, in the GP domain, what we do is maximum marginal. We'll see why it's called marginal likelihood estimation. Okay, or we can also compute the posterior distribution. But in a Gaussian world, it turns out that all of these will be exactly equivalent. Okay, so again, what I want to, at least from my experience, what I would say is GPs are not doing some sort of voodoo or something, something entirely different from what's known, but they do it. They use the power of Gaussians to kind of bring a lot of these characteristics under one umbrella. That's the way I look at it. Okay, fine. Now the question that you asked, kernels. Okay. Basically, they model the relationship between random variables. So if I'm, for example, if I'm estimating, if each of us is estimating something, say I'm measuring my height and you're talking about your height, okay, what I'm effectively encoding through these kernel functions is how is his height or his measure of his height correlated with mine. Okay, or how is your height correlated with mine? So if you have a spatial field of random variables, okay, it is saying how correlated are those random variables. That's what your kernel function is encoding. Okay, so yeah, so the point is, by definition, you require that this covariance matrix has to be positive semi-definite. So you take any real vector, you do an A transpose covariance matrix A, it will be greater than 0. Okay, or you have a problem for sure. Okay. Another interesting and useful thing that we will leverage later on is some properties of kernels. So if you have a kernel or covariance matrix, okay, some products or convolutions of these will also be covariance matrices. Okay, we'll come back to this. We'll use this at a later point. Okay, it's a very interesting thing to know. Okay, now there's an entire chapter dedicated in this book, okay, on this particular topic. Okay, we'll use a few of them, and I'll introduce you to those few of them, but there are many of them. There's a huge family of them. Okay, so probably the most popular and the first go-to kernel, if you want, is the square exponential or square exponential kernel. Now, this square exponential kernel is you can otherwise call it the Gaussian kernel. Okay, so if you look at the form here, it looks like a Gaussian, doesn't it? Okay, the same old covariance matrix. There's a distance measure between between points of interest. Okay, there is this sigma here, which in a Gaussian, it used to be called the covariance matrix. Over here, we encode what are called length scale parameters. Now, I'll explain what these length scale parameters are. But essentially, think of Think of that image of a multivariate Gaussian that we saw earlier. Okay, that's exactly what this is. Quite simply that. Okay, to visualize it. Okay, now what are these length scales? Okay, this sigma encodes what are called length scales. They basically capture the broad trends in your data. Okay, so in a parametric model, okay, if you're modeling a line, you would end up saying y equal to mx plus c. What are my values for m and c, right? Okay, over here I'm trying to capture instead of specifying m and c exactly, I'm going to specify a family of m's and a family of c's. Okay, so what trends of m's are applicable to me, or what trends of c's are applicable for my data? That's what these things capture. So it's one level up. Instead of specifying a parameter, you're specifying a family of those parameters. To specify that family, you need a parameter. That's what this is. Okay, so it's one level up, pushing it up, one level up. That's why it's called hyperparameter. You don't specify a single function, you specify a family of functions. Okay, so in practice, if you consider the terrain modeling scenario, okay, where I had x, y, and the elevation at those points, Lx and Ly would tell me how rapidly does my data change in my x direction and my y direction, for example. It doesn't tell me the exact function. It tells me broadly how quickly or how smoothly or how abruptly does the data change in the x direction and the y direction. Okay, and the additive Gaussian noise that we talked about earlier, we can kind of club it over here and add a signal variance, just for giving us additional degrees of freedom when we model the data. The parameters that we'll have to find out are the sigma f, sigma n, Lx, and Ly. Those are the parameters that we need to model or learn when we actually learn a GP for a given data set.
Delta is also a hyperparameter.
Sorry?
Delta, sigma squared delta.
Yeah.
Delta is also a hyperparameter.
No, it's a Dirac delta function. So it basically, you apply it along the diagonals. Yeah, okay. Yeah, so, so the Mattern, okay, so the thing about a Gaussian is that it is really, really smooth. Okay, it's infinitely differentiable, very, very smooth. Okay, so there is you don't need to know the formulas in detail, you need to understand what those formulas tell you. Okay, so for example, the thing that you need to pick up about both these functions which I'll talk about is that they are functions of x minus x dash. That's an important thing. Okay, because they are functions of distance, okay, and not the points themselves, even if you move the kernel somewhere else, the shape will remain the same. That's why it's called stationary. Okay, right. Now the Mattern, okay, this Mattern function, okay, there's a broad family of functions called the Mattern class of functions, okay, which if instantiated, I mean, for specific values of nu over here, you get different kernel functions. There's a particular kernel function that I'll talk about, which is the Mattern 3x2 kernel. Okay, now these are quite similar in some ways, okay, to the square exponential, and different in others. So in the sense that they are not infinitely differentiable. Unlike the square exponential, they are not infinitely differentiable, they are finite differentiable, okay, which is decided by the value of nu. Okay, it's decided by the value of nu. Okay, think of it as a stationary kernel, which is less smooth, okay, than the square exponential. Okay, that's at this point, let's think of it that way. Okay, what's important here is again to notice that there's a product of a polynomial function and an exponential function. That's something you want to observe. And there's this RK term over here, which is basically also a distance. So effectively, okay, the Mattern is also a function of the distance between points. Okay, this is something you need to pick up. Both these functions, both the square exponential and the Mattern, okay, are somehow a function of exponential to the power of minus RK, or minus the distance, effectively meaning that as you go away from me, you become less correlated with me. That's what it's encoding. Okay, happy with that till now? Okay, yeah. Okay, now here's another function. Okay, this is something I've used a lot. Okay, and I would, for complex data sets, I would definitely go with this particular function. It's called the neural network kernel. It's non-stationary. Why is it non-stationary? If you look at the form, okay, again, the sigma is, we'll find out what the sigma is. We'll learn the sigma parameters. But essentially, it's a function of the dot product between points. That's what you need to pick up, the x, and there's an x dash. Okay, there's a dot product over there, and it's a function of that. So it's a function of the absolute coordinates, meaning it's dependent on the origin. Okay, meaning if you move the kernel somewhere else in your coordinate frame, it's going to change. It's not going to be the same. Okay, and that's why it's non-stationary. Okay. So why, instead of x and earlier I was using x and x dash, why am I using x tilde and x tilde dash? Okay, because they are augmented. Now, how many of us are happy with neural networks? Okay, so shall we have a very quick idea as to what a neural network is? Maybe that helps. Yeah? Yep. So this is a one-slide introduction to what a neural network is. Okay. So you have data. Okay. They've been studied for very, very long time, decades. Okay. They've been used. Essentially, they were motivated to model human intelligence. Okay. Essentially, think of it for our purposes. Okay. You have data, input, output. Okay. You're modeling it. Your function here is represented by this network. Okay. Where your inputs are x1 to xd. Okay. D-dimensional input, which you feed in over here. Each of these inputs gets multiplied by a weight and comes into this node. Okay, you may apply some nonlinear function if you want over there, no problem. Okay, actually it's applying those nonlinear functions that actually enables it to model different data sets, but nevertheless, each of these inputs gets multiplied by a weight, gets, all of them get added up in this node, then you treat it with a nonlinear function, and then it goes to the next layer. So you have an input layer, you have an output layer, you may have one or more hidden layers. Okay? Each of these layers is also subject to what's called a bias. Okay? So it's just an additional degree of freedom that models, that kind of captures data that you're not able to capture through these weights. Okay? So these biases are feeding into each of these nodes. So every node in the hidden layer takes a weighted function of each of your inputs and a bias, adds all of them up, multiplies it, treats it to some nonlinear function, okay, and sends it to the next layer. You may have one or more of these layers. That's your neural network. Okay, quick introduction.